Hello, let's have a look at your B5 revision. So in question 1, you are given a circuit with 4 lamps connected, 2 on the first loop, 2 on the second loop. So if you look, I've used green and pink. So charges will either take this top loop and go through the top 2 bulbs or go down through the bottom 2 and back round. It tells you that the current flowing through lamp I is I. So because you have 2 lamps in series, each branch is effectively worth 2R. So if they're all worth resistance R, each branch has a resistance of 2R. The lamps are then rearranged using the same cell. You can actually see the same pathways are possible for charges though. So if you look, the charges can either go through the cell and through 2 lamps on the right, or they can do the same on the left. This is actually the same circuit if you look. It's just a loop where you can go through 2 of the light bulbs. Those are the same possibilities. We know that current is equal to the voltage dropped, the potential difference, divided by the resistance. So we have 2 circuits with 2 loops each, 2 lamps in series, both with resistance R. The resistance of each loop is the same. The voltage supplied to each loop, both before and after, is exactly the same. It's whatever the cell is able to provide, V. So we know that if I is V over R and the voltage supplied to these 2 lamps is the same in both circumstances, which it is, and the resistance on each loop is the same before and after, the current will also be the same. So it's just a different drawing of the same setup. And that gets you to the same current I. In question 2, it says 2 resistors of equal resistance R are connected with 2 cells of EMF epsilon and 2 epsilon. Both cells have negligible internal resistance. So you can see the first thing I did, if I zoom in a little bit, is I've labelled up my circuit. So I've got my positive terminal of my power supply. So I have current coming out of both. I don't know why I did it 1 on the right and 2 on the left, but it doesn't really matter. I1 is being drawn from this cell. Okay, I2 is being drawn from this cell out of the positive terminal. So obviously I2 will flow through component X. At this junction, I1 and I2 join together. So flowing through resistor R is the sum of I1 and I2. That then splits again, I1 goes back round to the right, I2 goes back round to the left. You're asked, what is the current in the resistor labelled X? So I am looking for the value of I2 because that's what will flow through X. So, let's see if I can fit everything. This might be too much to try and do everything all at once. Right, let's see if I can just do this bit. So, I'm just going to look at the loops. So I've labelled loop 1 as pink and loop 2 as blue. We know from Kirchhoff's laws the sum of the EMFs around the loop will be 0. So we know that whatever the voltage gained is across the power supply, it will be dropped across the circuit so that the potential value of a charge leaving the power supply will be 2E, but it will be 0 by the time it gets back round. Okay, so for loop 1, I can say that a charge picks up 2E, the EMF, and then it has to drop that across the circuit. But we know that voltage is equal to IR, the current flow multiplied by the resistance. So in loop 1, the current flow through the resistor was I1 plus I2. So that's why I've got I1 plus I2 here. And then I'm multiplying by R. So I know that I gain 2 E. I then lose I1 plus I2R. So plus minus has to add up to 0. So I can rearrange that and say that 2E is equal to I1 plus I2R. In loop 2, we only gain EMF E this time. I should say epsilon, but I'm just being lazy. Okay, I gain E as I go through the supply. I then have 2 voltage drops. The drop across X and the drop across R. The drop across X, the voltage V equals IR, will be equal to the current flowing through, which is I2, multiplied by its resistance R, which we're told. And then the drop across R will be equal to the current through R, which we said was I1 plus I2, multiplied by R. So I know that in loop 2, I gain an EMF, but I drop two different voltage values, and that I know the sum of the loop has to equal 0. Okay, so that's where I got to. So if I come down here now, that's a bit better. Okay, I'm going to take my expressions 1 and 2. So I have an expression for 2e from loop 1, and I have the ability to sub loop 1 into loop 2, what I know for loop 1 into loop 2. So I know that I have E minus I2R minus I1 plus I2R equals 0. But I know that I1 plus I2R is also equal to 2E from loop 1. So I can replace this term in loop 2 with 2E, which is how I get to this line. I can combine like terms. I've got E minus 2E, leaves me with minus E. I can rearrange for E. The negative sign then just represents direction. It doesn't really matter. The magnitude of I2 is then just E divided by R, which gets me to C. Okay, I'll just zoom out a little bit if you need to pause here. Okay. In question 3, so a variable resistor is connected to a cell with EMF E and internal resistance R as shown. When the current in the circuit is I, the potential difference measured across the terminals of the cell is V. So immediately I start writing my equations that are going to be helpful, and I rearrange them into forms that I might want to look at. So I have EMF is the terminal PD plus I little r, where little r is the internal resistance. I've then just written a list of things. So initially we have a value of R, little r, and a value of big R. The resistance of the variable resistor is doubled. So I immediately know if it's a higher resistance resistor now, it's going to demand a greater share of the EMF. And so I know to get rid of C and D already. I already know that the voltmeter is going to read the voltage drop across this resistor, because it's measuring before and after. It's going to be a larger value. Okay. I then can look at the current, and the way that I did this was I got two expressions for current, and then I just thought about plugging in an example. So you will see that I've rearranged my EMF equation to say that current flow is equal to EMF divided by the total resistance of the circuit. I labelled big R for the resistor down here. I know that then the variable resistor resistance doubled, so this became 2R. Okay. Now all I did to check whether the current would be greater or less than I over 2 was I chose two arbitrary numbers. Any would work, no problem. Okay, so I said let's say that originally internal resistance was 2 ohms and the variable resistor was 4 ohms. I then just substituted in here. So initially I had E over 2 plus 4, so E over 6. I know that what I'm trying to do is know whether the value is going to end up being greater than half of that original value or less than half of that original value. Okay, so I took that original value and I halved it to see what that would be, and I got E over 12. I then calculated what it would be once this doubles. So this obviously would go from 4 to 8, which then makes this E over 10. E over 10 is a bigger number than E over 12 in magnitude, and so I choose A. It's the easiest, quickest way to get to an answer there. In question 4, a cell of negligible internal resistance is connected to 3 identical resistors. The current in the cell is 3 amps. The resistors are now arranged in series. What is the new current in the cell? Okay, so I immediately tried to look at the total resistance of the circuit. So the pink section, if I just grab my pen, is me just looking at this section. Okay, and I combined in parallel to see that this is worth R over 2. So the total resistance is R plus R over 2 gets me 3 over 2R. Okay. The circuit was then rearranged and put in series, and I know that they're each worth R, so the total resistance would become 3R. So by rearranging the circuit, I went from a total resistance of 3 over 2R to 3R. Okay, you should be able to see that the resistance has doubled. Okay, it went from 3R over 2 to 3R. The resistance doubled. I is given by V divided by R. If R doubled but V stayed the same, then I has to have halved. You're told initially it was 3 amps, so half of that is 1.5. Okay, in question 5, let's see if I can get the whole thing in just about. Okay, so in the circuit shown, the battery has an EMF of 12 volts and negligible internal resistance. 3 identical resistors, so I can label them all as R, are connected as shown. And actually we're told that they have a resistance of 10 ohms each, sorry. Actually, that doesn't really matter. You can purely just do the fact that you know they're identical. So they've kind of been helpful here by listing that this is the positive side. So at this point, a charge has 12 joules per coulomb, whereas once it's at this point, it has 0 joules per coulomb. So I find the effective resistance of this section because X comes after this junction recombines. So each worth R, together R over 2. That's just using your combining resistors in parallel equation. I know that this one is worth R. So this section has half the resistance of this section. Half as difficult to get through. It will demand half the voltage of this one. So I know that if I'm a charge leaving this cell, I have 12 volts. I have 12 joules per coulomb of potential. Okay. At this point in the circuit, nothing has happened yet, so the charge still has a potential of 12 volts. Once it travels through K or L, its effective resistance that it's travelled through is R over 2. It has taken half the amount of the voltage that M will take. Okay, so this will take 4 volts when this will take 8 because this section is doubly difficult than this one. So as a charge moves through either K or L, they will drop 4 volts in potential. Now at this point in the circuit, they had 12 joules per coulomb. If they drop 4 volts, it means that they now only have 8 joules per coulomb to transfer in the rest of the circuit. So their potential value at this point is now 8. Once they go through M, they're at a potential of 0. The resistor L is removed. What is the change in potential at X? So what is the joules per coulomb value of a charge at X? So now we only have K and M. We know they're identical in value, so they will take a 50-50 split of the potential energy. So we know that a charge with 12 volts of potential at this point is then going to drop 6 volts here. 6 joules are transferred per coulomb through K, and then 6 again through M. But in terms of potential at this position, they started with 12, and then when they went through K, they dropped 6. So they are at 6 volts. The change in potential at X is that it went from 8 to 6. It decreased by 2. Okay, in question 6, 2 cells are connected in parallel as shown below. Each cell has an EMF of 5 volts and an internal resistance of 2 ohms. I've labelled it as epsilon and R. The lamp has a resistance of 4 ohms. The ammeter is ideal, so takes none of the voltage share because it's no resistance. What is the reading on the ammeter? Okay, so when cells are connected in series and each of them is worth a certain amount of voltage, it's really straightforward because a charge will go through both, and so that just adds up in series. That's worth 6 volts. When cells are connected in parallel, though, the charges will only ever go through one and not both of the cells. And so from one side of the circuit to the other, the charge will only pick up the voltage that one of them is able to supply. So let me come down here, and I've written cells in parallel are actually equivalent to one cell providing the same EMF but with lower resistance, and that's because there are now more pathways for the charges to get across the circuit and gain their potential energy as they move through that cell. So we were told in the question the internal resistance of each of the cells was 2 ohms. Charges will pick, from this point to this point in the circuit, will pick up 5 volts. They will either go through the top one or the bottom one, but by providing more pathways, we lower the effective resistance and we combine the resistance of these two like we would in parallel. And we can see that that means that these two cells in parallel are worth 1 ohm. Okay, so I've now redrawn the circuit. If you go from here, what I've done is I've said the effective resistance of these two is a 1 ohm resistance cell that is able to provide each charge with 5 volts. That is then in series with the light bulb, which we're told is worth 4 ohms. Current flowing through a series circuit is the total voltage supplied divided by the total resistance of the circuit. The total resistance of this series circuit is the 4 plus the 1. The voltage supply was 5, and therefore the current is 1 amp. In question 7, a circuit consists of a cell of EMF E is 3 volts and 4 resistors connected as shown. R1 and R4 are worth 1 ohm, R2 and R3 are worth 2 ohms. What is the voltmeter reading? So remember, the voltmeter is saying, okay, if I reach in at this point, how much energy does each charge have at this point in the circuit? And then at the other end, how much energy per charge do I have at this point in the circuit? What's the difference in how much energy per charge we have between these 2 points? So the first thing is, for my brain to handle this, I need to redraw this in a way that I work with. I don't like the diamond. If you're happy with it, that's fine. But I suspect that because I prefer it like this, some of you may also do so as well. So again, it's about tracing loops. So if a charge comes out of the cell, at this junction, it will either go through R1 or it will go through R2. If it goes through R1, it will then go through R3 and come back round, okay? We know that it can also go through R2 and then go through R4 and come back round, okay? The voltmeter is a measuring instrument. It's not an integral part of the circuit where current is flowing. So we know we have 3 volts and there are 2 possible routes around the circuit. I can go through R1, R3 and back, or through R2 and R4 and back. I've drawn it out in a way that I'm happy with, and I'm now going to work out what the voltmeter is reading, which means I need to know how much potential is here per charge and how much potential is here, because this is where the arms of the voltmeter were connected in between R1 and R3 and R2 and R4. So if I know the 2 values of voltage, which I'm going to look at in just a second, I just find the difference, and that gets me the voltmeter reading. So I have 3 volts from my supply. I've got a 1 ohm, a 2 ohm resistor. Doubly difficult, double the voltage share. So 2 ohms takes 2 volts, 1 ohm takes 1 volts. Other way around on the bottom loop. So we drop 1 volt across R1. We drop 2 volts across R3. A charge leaving the supply has 3 volts of potential at this point. Before going through R1, the charge is at a potential value of 3 volts. It transfers 1 volt across R1, which means it's now left with 2. If I were to take the second path, the charge would have 3 until this point, 3 volts, 3 joules per coulomb. It would then transfer 2 volts, drop 2 joules per coulomb, moving through resistor 2, meaning at this point the potential is only 1 volt. The potential difference between these 2 points is 2 minus 1, gets me 1. Okay, in question 8, 2 wires X and Y are made of the same material and have an equal length. The diameter of X is twice that of Y. What is the resistance of X compared to the resistance of Y? So you're finding the ratio. We take our resistance equation, R is rho L over A. L is the same for both, so I'm really only interested in the A proportionality statement. Rho is the same for both because they are the same material, so I can say that the resistance of each wire is inversely proportional to the cross-sectional area of the wire. We know that the cross-sectional area is a circle, so the area is found by pi r squared. R is d over 2. If we do d over 2 squared, diameter over 2 all squared, I get pi d squared over 4. Pi and 4 are constants, so they're not going to affect the area. The diameter squared will affect the diameter, the area. So area is proportional to diameter squared. What that means is, if resistance is proportional to 1 over area, then it is also proportional to 1 over d squared. Now, in the question, we are told that the diameter of X is twice that of diameter of Y. If AX is proportional to dx squared, which we've just said it is, and AY is proportional to dy squared, which it is, then I can say that AX must be proportional to 2dy squared, which means I've got AX is proportional to 4dy squared. Therefore, AX has to be 4 times larger than AY. I know that the resistance is inversely proportional to the area. So if the area of X is 4 times that of AY, then the resistance of X is 1/4 that of Y. Okay, so that gets me down here. So I've said that Rx is proportional to 1 over AX, which is equal, AX is equal to 4AY. Ry is proportional to 1 over AY. So if I look at the ratio of Rx to Ry, I'm just replacing, because it's all proportionality statements, Rx was 1 over 4AY, Ry was 1 over AY, the AY's cancel, and I'm left with 1/4, getting me answer A. Almost there. In question 9, 2 conductors S and T have the VI characteristic graph shown below. So you've got current and voltage for S and T. So when the conductors are placed in the circuit below, the reading of the ammeter is 6 amps. And you're given the circuit diagram. And it says, what is the EMF of the cell? Okay, so the ammeter is reading the current that has come from S and T. So IS plus IT must equal 6. The only point on this graph where the current of S plus the current of T equals 6 is this point here. Okay, so we know that it's a 3 and 3. Anywhere else, and the numbers don't add up to 6. What that means is the voltage across S and T were 4 volts. This is also helpful because we can quite clearly see that VS has to equal VT because they are in parallel. So it is the only point on the graph that you should be reading. Okay? The EMF of the cell is the voltage supplied to both S and T, which we know from the graph is 4 volts. Therefore, it is A. In question 10, a circuit contains a variable resistor of maximum resistance R and a fixed resistance, also of resistance R, connected in series. The EMF is 6 volts. The internal resistance of the power supply is not important, negligible. What are the initial and final voltmeter readings, so the voltage drop across this top resistor R, when we start from the variable resistor being 0 and it ends at R? Okay, well, if this is 0 ohms, it doesn't demand any voltage share. It has no resistance, which means that the entire voltage of the supply can be dropped across this top resistor. So initially, I know I have 6 volts. As I steadily increase the resistance of this up to the value of R, I have one that's R here and one that's R here. They are equally difficult for charges to move through. They will take an equal share of the 6 volts, so they will take 3, getting me to C. Question 11, you can see they love the proportionality statements. You've got 2 wires. This time, though, it's more complicated because L, rho, and A are all variable. So the resistance is proportional to the resistivity, the resistance is proportional to the length, and the resistance is inversely proportional to the area. I'm going to write down everything I know from the question. The length of y is 2 times that of length of x. The diameter of y is half of the diameter of x. The resistivity of y is half the resistivity of x. I know that my resistance comes from cross-sectional area being involved, so I'm going to take my diameters and look at how the areas must be different. Area is pi r squared. Pi times d over 2 squared, which is pi d squared over 4. So I know that the pi and the 2 are constants, so ax is proportional to dx squared, ay is proportional to dy squared. Okay. I know the relationship between dx and dy, so I can replace dy with dx over 2. Okay, so I get the factor difference for ax and ay. So if ax is proportional to dx squared and ay is proportional to dx squared over 4, the area of y must be a quarter that of x. What I'm then doing is I'm going back to the ratio that I'm asked for, Rx over Ry, and I'm replacing R with rho L over A. That's the equation for resistance. Okay, straightforward on the top and initially straightforward on the bottom, but I'm going to replace the values for Y with what they are equivalent to with X. So rho Y was equivalent to rho X over 2. Ly was equivalent to 2Lx. Ay was equivalent to a quarter Ax. I can cancel the things that are on the top and the bottom, and all I'm left with are my scale factors. I simplify to get to a quarter. Okay, question 12. In the circuit shown, the cells have the same EMF and 0 internal resistance. All resistors are identical, so I've just called them R. So I found the total resistance of each circuit. You can pause, you can have a look, but you should be able to do that. We've got R over 2, 2R, and 3R over 2. I know that power dissipation comes from V squared over R. The V supplied in each circuit is the same. The resistance, however, is not the same. So P, power dissipated, is proportional to 1 over R because V squared is constant for all of them. So all I have to do then is look at how resistance goes from highest to lowest, and that will then give me the power from lowest to highest because power is inversely proportional to resistance. So I'm literally taking these numbers and putting them ranked from highest to lowest. So 2R to 3 over 2R to R over 2. And I know then that the power dissipation is in the opposite direction to that, and that gets me to A. Hopefully we're on the last question. Yes, we are. Okay, so resistor R is connected in a circuit with a cell that has internal resistance. The ammeter and voltmeter are ideal, so they're not going to contribute anything to the circuit. They're just going to make measurements. The cell has an EMF of 1.49 volts. The resistance of R is 50 ohms. The voltmeter reads 1.47 volts. So I can work out the current flow through R by looking at the voltage dropped across it divided by its resistance. We know that the voltage drop across the circuit is 1.47 volts and that the resistance is 50 ohms. So I can calculate the current flowing through. Okay, sorry, I forgot to cut this picture. It's because in the previous syllabus, this bit was part of the electricity topic and it no longer is. So, in A, state what is meant by an ideal voltmeter. no current would flow through it, so it would have to have infinite resistance. That's just one to know, we wrote that down. In B, show that the internal resistance of the cell is about 0.7 ohms. So I'm going to take the equation EMF is equal to terminal PD plus the lost volts, which comes from V equals IR, the current flowing through, multiplied by the internal resistance. Then it's just a case of substituting numbers in, and it's algebra, rearranging for R. Note, you have to give to more decimal places than they say, otherwise you're not proving anything, okay? Don't just jump straight to 0.7 there. And then the very last thing that you were asked to do to determine the total power dissipated in the circuit, we use P is V squared over R. We know from the question that the total power comes from the voltage value provided by the EMF, 1.49 squared, over the total resistance of the circuit, which is the resistor value, which was 50, plus the internal resistance that we've just worked out, 0.7, and that's how you get to your final answer there.